So, let's start again.
Yes. Yeah.
And, well, first of all, disclaimer. My previous research was mainly in evolutionary robotics, and I was studying the way to synthesize self-organizing behaviors for a group of robots. And within this research thread I was studying how it's possible to have collective intelligence, what does it mean to have collective intelligence, and so on. Everything exploiting the automatic synthesis of behaviors given by evolutionary robotics. Given that the goal of this series of seminars organized by Storns is to get in touch and maybe have feedback and promote collaborations, I decided not to talk at all about my previous research and to start talking about what I'm doing right now. The problem is that this is really work in progress, so I don't have the most beautiful results to show you, but a lot of ideas and a lot of ideas that are based on the study of the literature. So I will present these ideas and the work that I'm doing right now. So there are some results, not so many, but I hope that I will stimulate your interest, and maybe if you want to interrupt me and give me feedback or afterwards, if you want to start a collaboration, I'm open for that. So the goal of this is really showing you what are my ideas right now and trying to foster your interest and collaborations. I will talk about this idea of swarm cognition and how to pass from natural to artificial systems, and possibly how to feed back some knowledge to biological systems. A brief outline. This seminar is divided mainly in two parts. In the first part, I will give you the theoretical basis of swarm cognition, and then I will talk about how to exploit these theories in order to design, to engineer artificial systems and distributed cognition in artificial systems. And then, of course, some conclusions. So, what is swarm cognition? This is basically the juxtaposition of two concepts: the idea of collectives, of complex systems made by a lot of individual units that interact a lot to have, in the end, a coherent group behavior, and the idea of cognition that is, well, difficult to give a short definition, but say that we can think of cognition about some form of information processing, of making sense of the information that is gathered through the environment in order to promote some intelligent adaptive behavior, survival in the most simple system, and then making decisions, categorizing the world, communicating with other agents, and so forth. There is actually, it could be strange to think to these two concepts together, but in the end, if we think about it, our intelligent behavior comes out from a complex interaction in between a network of neurons that are very simple units. And of course, there is the body that mediates the interactions of the neural system of the brain with the environment. But why not thinking towards work as a collection of units that can interact with the environment, can display then cognitive behavior? So the idea started more or less in this way, and I started to dig into the literature to see what was available. And actually, I was definitely not the first one to have to recognize this parallel. And of course, the first thing you hit is the idea of a superorganism, which has been developed in the last century. That is, the superorganism is a collection of simple units, simple organisms, like ants in a colony, that are so tightly linked one to the other that can be thought of as a single big organism that makes decisions, that has a reproductive activity, has a foraging activity, has a metabolism, and so forth. If an individual organism, like a human being or even any mammal or an insect, can cognitive system, then why not keep ascribing cognition to a superorganism as well? And here we have to understand many different things. What does it mean to talk about cognition in the context of superorganisms? What is the body of the superorganism that mediates the cognitive activities of the system with the environment and so forth? There are partial answers in the literature, and I want to start with this idea of extended embodiment by citing, by describing you the work of Jason Scott Turner in a paper that is called Termites Models of Zone Cognition. I want to start from here because basically here we can see that there exists a superorganism and there exists this concept of extended body because the nest of termites is an active part in the activities of the colony. Here you can see two pictures, a picture of a nest and on the left there is actually the structure of tunnels and galleries of the nest. This was built by putting some plastic liquid that could solidify afterwards and then destroying all the ground and leaving only the traffic part. And you can see how intricate is the network of galleries that these insects are able to build. Remember that termites are very small, are blind, are very simple insects, but in the whole they are really magnificent architects in order to build this. What is the function of this? Well, think that a termite colony comprises millions of insects. There are also a symbiotic fungi that live in a connection with the colony that serve to pre-digest the food which the termites forage. And in total, the biomass of this symbiotic system in between termites and fungi is about the size of a goat. So it means a big mammal. You have to understand the metabolism of this system is quite rich and important. And for this to happen, you need some gas exchange with the outside. You need oxygen, and you need to expel your gases. And actually the mound is what does this for the colony. It's a mediator. It's like the lungs of a mammal, and it has a complex structure like the lungs of the mammal. What's the function? Basically, the mound is a tall structure, 2 meters or tall, even more, which can intercept turbulent winds. These winds are made up of a lot of AC components, and therefore what the mound does is to filter out the turbulent components and to let it's kind of low pass filters, to let only the slow components arrive into the deep of the nest, so that in the end, in the lowest part where the colony really lives, what arrives there are just puffs of air which allow this exchange of gases on the colony. This is the function, but then what has been shown by Scott Turner is that this filtering of the turbulent wind can be exploited by termites to drive the building and the repairing activities of the nest. So if the nest is damaged in some point, the insects are blind, they cannot see where actually the damage is. So what they can perceive is a change in the filtering of the turbulence, that is the high frequency turbulence can arrive deep into the nest, so they are driven by this to the place where repair is needed, and they start building more or less randomly. So they make a lot of hypothesis testing of building to repair the nest, and after a while some of the structures that are built are destroyed, and the correct one, the one that provide the final filtering, are maintained and refined. This is to say that even termites in their construction activities, they make some sort of decisions they make some decision on where to build, how long to build, how big the structure to be built must be. And if we manipulate a nest of termites, then you can create some kind of cognitive disorders into this extended cognitive system. For instance, if you insert a pipe into the nest, which will let the wind arrive deep into the inside of the nest, then the termites will start building and will start to block the inside of this pipe. But what happens is that they will never stop, and they will fill completely the pipe, even if it is 10 kilometers long, because there is some kind of this cognitive disorder. The pipe is not something natural that termites can encounter in the natural system. Above all, it does not let the pheromone to evaporate, and the construction activities are mediated by pheromone, which means that if the pheromone stays there, does not evaporate, then the construction activities will continue. It is sufficient to make some holes in this pipe to have back a normal behavior. Scott Turner talked also about zoomorphasia, that is the insensitivity of insects to certain external stimuli, which are given by a sort of habituation of the behavior. So basically, this is just to give you a hint. You can find everything in the paper that I was citing. Just to give you a hint that complex societies like the one of termites can present a very complex behavior, even if the behavior of the simple individual is very basic, very simple. And basically also to give you the idea of the interaction with the environment that is mediated by the nest. So the nest is something very important for social insects. And let's then the decision on where to build the nest is fundamental for the survival of the colony. That's why the decision-making process to select a nest is a very complex one, and actually it has been studied into deep to find the details, and to show also that this decision-making process is equivalent to decision-making done in the brain. I will arrive to that slowly. We will first describe a little bit how does it work. When a colony needs to emigrate, so it needs to find another nest, normally it creates a swarm on the branch of the tree or somewhere where the queen resides, and the swarm self-assemble in this structure in order to ventilate, to create the correct temperature and humidity inside the group. From here, scouts bees depart in order to search for a nesting site. And each bee can explore a radius of something like 5 kilometers, so it's a very wide area. And when it finds a hollow tree, for instance, where to nest, the bee inspects the site and comes back to the swarm to give the evaluation. At the swarm, the decision-making process takes place, mostly at the swarm. There is part of the decision-making process that takes place also at the different sites. But basically, the most important part happens here. The scout bees comes back to the swarm, they make their battle dance to advertise for the nest they discovered, and recruit other bees that go out and visit the nest, inspect the nest, make their own evaluation, and go back to the swarm and replicate the process. This recruitment and evaluation, individual evaluation, drives the decision making, because recruitment is stronger for better quality sites, which means that after a while, this process can last a couple of days. After a while, the swarm takes the decision for one single option, which normally is the option in which a certain number of bees stay, because decision is taken when a certain quorum is reached at one of the alternatives. At that point, there are some buzzing signals that let the swarm take off, and then they inform the individual that know the place where they have to go. They fly fast through the swarm in order to drive the collective motion of the group, and then there is a emigration of the whole swarm to the different side. This is what has been studied mainly by Tom Seeley. I remember where it is. Models are available. There is a lot of knowledge about that. There is an interesting paper by Passino, Seeley, and Fisher, which is called Cognition Analogies, in which they make a parallel in between distributed cognitions, one cognition, and the cognition, the activities into the brain. So they make a comparison in between an individual B, which is analogous to what a neuron does. The individual quality assessment of a B, it's like the activation threshold in a neuron. The vital dense corresponds to the action potential of neurons. Then the population of bees that are committed to a site is analogous to a population of neurons that coherently behave. If we take all the groups of committed bees, well, this is a representation of what the environment looks like in terms of available nest sites. And this is analogous somehow to a short-term memory about what has been experienced by an individual. Cross-inhibition in between bees exists, and this can be thought of as the lateral inhibition in between population of neurons. And finally, this can go on even more, but I just conclude with the exploration for potential sites. When scouts go out, they sample the environment for the properties of the environment. Well, this is analogous somehow to the attentional processes for individual cognition. Okay, everything very beautiful, but give us something more interesting, because these are just analogies. It is possible to go beyond analogies if we look into the specifics of these decision-making processes. Actually, nest site selection in honeybees and also in the rock ants, these ants are small ants that live in small colonies of about 100-200 individuals that nest in cavities in between the rocks, which are very flat. So they are perfect model insects because they are very easy to study. You can replicate their nest in 2 dimensions in the lab, and there is a lot of literature on that. But basically, they do also immigrate. They do also have a decision-making process to select the nest where to site. So if we can study the dynamics of the decision-making, these two model insects, and it is possible to demonstrate that there is functional equivalence in between their process and decision-making into the brain. In particular, what has been shown by Marshall et al. Is that there is the ants and the bees implement somehow an optimal trade-off in between the speed of taking a decision and the accuracy of the decision itself. That is, if you have to evaluate a noisy environment, noisy alternatives, you need to collect information about all the possible alternatives, and this process takes time. So you have to take this, you have to select the correct trade-off in between a fast but not accurate decision and a slower but more accurate decision. There is therefore a trade-off, and you can face this trade-off optimally by taking the minimum available time for a given accuracy. Ants and bees do that. How do they do that? Well, to demonstrate this, it's useful to introduce something about optimal decision making. Basically, what has been shown with the psychophysical experiments is that we can model optimal speed accuracy trade-offs by means of a diffusion model, which was proposed by Ratcliffe and Smith. And this diffusion model basically tells us that a decision between 2 alternatives can be modeled as a Brownian motion with some drift in the direction of the better quality alternative, so that the more you accumulate evidence about the quality of the different alternatives, the more your level of satisfaction with one or the other alternative varies, and this is like a Brownian motion, with a random motion, with some drift that is given by the difference in quality between the two alternatives. As soon as the threshold is reached, a decision is made. By varying this threshold, you can vary the accuracy of your decision making, which means that a smaller threshold will let you reach your threshold faster, but with a lower accuracy. Basically, studying this, you can illustrate that this is a special case of a sequential probability ratio test, very known in statistics, because it exploits the Pearson-Neumann lemma, and this ensures that the choice you make is optimal. It gives you the optimal choice in the shortest time for a given accuracy. These are the theoretical basis that tells us that decision making can be optimized the speed accuracy trade-off. Now,
Vito, can I interrupt?
Yeah.
So, to summarize, this gives you a one-parameter family of solutions which are optimal.
Mm-hmm.
So, but there is no way to define, for the reason I'm asking you, to define just the optimal solution. So, if you really define something.
Well, there are different possible models and different possible implementations of this model at the microscopic level. I will write this soon, but it is not given that they implement a sequential probability ratio test. That is, they are optimal in this sense. You can test you can make this test, a statistical test on the decision and verify it or not, or reject it somehow. So you have a broad family of processes that you can study, that you can observe and study in nature. What is interesting is when these processes are really optimal, which is not straightforward. So we are talking about what we observe in nature, and we are trying to see whether what we observe is optimal in this statistical sense.
Yeah, I understand that. What I would like to know if there is some way to define optimality so that you are fixing the accuracy and you're not letting the accuracy vary.
You do that every time you want to have a certain answer. I mean, for any level of optimality, of accuracy, you have a certain time required to reach that. So if you are beyond this time, if you go longer, then you are not really optimal. I don't know if
maybe in the case that you cannot direct to have a approximate solution, and so you have only one possible level of accuracy. In that case, the accuracy is fixed because when
because these are more or less the theoretical framework in which the study I'm presenting you is fixed. Now, given this theoretical discussion basis, what has been shown is that the decision making in the cortex can be reconducted to sequential probability ratio test. I will give you just some hints. Basically, the Asher-McLellan model is a model of decision making in the cortex in which there are two populations that are competing to give the correct answer. The populations receive input from the external world, say, with noise, and they interact by cross inhibition. And there is also a leaking factor, so they are leaking integrators somehow, these populations. You can model this with these systems of two differential equations, stochastic differential equations, which give the input, noise factor, leaking of the value, and cross inhibition. This is a quite simple system, but it's not straightforward to study. So basically, what can be shown is that you can do a variable change in this system by introducing these two variables, and you can rewrite the system in this way, which completely decouples the two variables. So you have two independent equations somehow that describe the process of decision making in the brain. You can see that there exists parameterization of this system in which the system implements an optimal decision making. If the cross inhibition factor is the same as the leaking factor, so if W is equal to K, then this term goes away, and what remains is Brownian motion with drift. And while these other factors tells you how fast you are to converge to these dynamics of Brownian motion with drift. So if K and W are big enough, the dynamics of this part are very fast, and therefore you can basically assume that they finish very fast, and then you can focus on that. What you can show is therefore that in the space of y1 and y2, the important dynamics of the decision are driven by around this line. If this equation is fast enough, the dynamics of these are fast enough, then quickly all the trajectories converge on this line, and then there is the Brownian motion on this line, so that a decision is made when a threshold, this one, vertical or the horizontal one, is made. But what is interesting is that actually there exists this parameterization that lets you tell that the system is optimal. Now, given this, what can be done is to show that there are models of the nest-size selection in organs and only these that present the same dynamics. To do this, it's possible to develop population-level models of nest-size selection in which you have a population of insects that can be committed to one side or the other side, and you can understand what are the flows in between these populations. So you can develop a model like this in which you have uncommitted individuals here and individuals committed to the option 1 or the option 2. And you can characterize the flows in between the different populations in terms of the independent discovery of alternatives, the scouts that go out and find the nest and come back, that becomes committed because they independently discovered it. You can, and this is basically this term, if I'm not wrong. Then there is the part of recruitment of uncommitted individuals. There is a scout that recruits another scout in order to visit the nest and get committed to the nest. And then there is some leaking, the spontaneous abandoning of commitment. To this you can also add the possibility of direct switch in between the two populations. That is, if one bee committed to the side 1 encounters a bee that is committed to the side 2, then one of the two may win the competition and let the other switch directly to being committed to the other side. By writing this population level model, it is then possible to directly switch to a system with differential equations. I will not go into the details because everything is on the figure that was set before. And basically you can study this, you can make the same variable change in order to see whether you can decouple the two processes, the one of the decision and the one of the speed of convergence. And it was shown that this is the model for organs. And it is possible to do that, but this requires very specific parameterization that involves all the possible variables. So it's not very likely that this happens into the natural system. If you do the same for a model of honeybees, which is different mainly for the fact of having or not the direct switch in between the two populations, then it was shown that yes, there exists a parameterization that let you prove that bees implement optimal speed accuracy, optimal decisions, optimizing the speed accuracy trade-off. And basically this happens when the decay rate is null, which means that when a bee gets committed, it never forgets this commitment. Eventually it can switch commitment. So what happens here is that all the dynamics of committed are very fast, all the population gets committed at some point, and then it is just a competition between the two options. And the direct switch allows you to pass from one to the other option, and finally one of the options will win. So what has been shown here is that there exists actually parameterization for the social insect models that let you claim that the collective decisions on a beast are equivalent to decisions in the cortex, functionally. The function that they make is the same, and they do it with the same dynamics. And this is an interesting factor because it is really a parallel. Now it's a well-grounded parallel in between the dynamics of decision into brains and swarms. But when you look at the cognitive abilities of swarms, then or cognitive systems in general, well, there are some common traits that can be recognized. One of these, we just continued. Basically, this is part of my work in progress. We just continued that research on decision making in organs and honeybees by trying to understand whether they present the same cognitive traits of other cognitive systems. And one of these we selected is the adherence with the Weber-Fechner Law. The Weber-Fechner Law tells us that there is a nice linear relationship in between the strength of a signal that is perceived by a cognitive system and the ability to tell the difference in between similar signals. That is, there is a just noticeable difference in between signals that is necessary to discriminate in between two different options. So if you have, for instance, to decide whether we have two weights, if one is stronger than the other, weight more than the other, then you need a certain difference between the weights to be able to discriminate between them. And this difference increases linearly with the weight. So if you have two weights of 10 and 11 grams, you don't tell the difference. In between 10 and 12 grams, you can tell the difference. But then if you increase of a tenfold magnitude and you pass to 100 grams, then you need 120 grams to tell the difference in between the two. So there is a linear relationship in between the difference in between two options, two alternatives, and the strength of the quality of the alternatives. This is what the Weber-Fechner Law says. It has been shown in a huge number of cognitive systems and perceptual systems, basically, in nature, not into distributed systems like social insects. So what we have done is to take the models of decision making in social insects and to try to verify whether they adhere or not with the Weber's law. To do this, we made Monte Carlo simulations of necessary selection with the two models I showed you before, and we try to verify this. And this is a long process because you have to iteratively do this. You have to fix the base quality of the option 1 and vary systematically the quality of the option 2. And then you have to identify the probability of selecting one option on the other. On this data, you have to fit a curve because you want to calculate the just noticeable difference in between the two options. And once you do that at a certain level of accuracy, which is selected as 85% in this case, you have this number. Then you do this for a number of times and you obtain your answer. So this is one case for one base quality. All the single dots represent the frequency of the decision made by the model, whether for option 1 or for option 2, basically. So 0 means that option 1 was selected 100% of the time, 1 means that option 2 was selected 100% of the time. If you do that by varying slowly the quality of option 2 with respect to option 1, then you have all this data. All these are Monte Carlo simulations. And then you can fit a curve on this. Once you fit a curve, you can find the 15% and 85% thresholds, which tell you that the case in which, with certain accuracy, you always select for one or the other option. Then the just noticeable difference is half of this range. And this is for just one way.
Yes, I want to know if to do this simulation you started from the equation of the decision making, the differential equation. And this equation were taken from the Asher model of 2001, no?
I'm working on the social insect model, so that is...
The equation of the insect that we used to take this result, it was taken from the Asher model.
There is
somehow an equivalence between these two models.
Under certain parameterization, not all.
Yes, and so my question is, there is a result in literature that show that the Weber law comes from the Asher equation.
I don't know about that. If there is a direct link
because maybe this kind of result comes from that kind of equation.
Actually, the microscopic mechanisms behind the Weber's law are not really clear. There is a paper by Deco that I worked on a little bit, in which it is claimed that in order to have a model that represents that adhere with the Weber's law, decision model that adhere with the Weber's law, you need a multi-stable situation in which you have, there is nothing to write, but basically, well, there is no prejudice initially there is no prejudice, so you have a little valley, say, in which your decision stays, and you have two hills that you have to cross in order to take the decision. If you are in this case, then you are there with Weber law. If you are not in this case, you don't. But it is not really clear to me, or at least this was, and the description of this result was not strong enough because it was just a suggestion. They didn't demonstrate this. And actually, I think that it is needed to give a better characterization of the dynamic factors that leads to adherence or not to the Weber's law before claiming that this model gives you advice. Also because what we found is that when we did this for ROCANs, so we repeated this process for a lot of different base qualities, and then we plotted them. We found actually the Weber's law, which is the linear relationship between the base quality and the just noticeable difference. And this was totally unexpected because there were no parameterization that led us to claim that the ROCAN's model was actually optimal. And we actually selected only one parameterization more or less at random. So maybe we were just lucky, and this is actually work in progress. But probably maybe the point in which you can say, okay, this is what gives you adherence or not to the Weber's law is still to be found.
This is a simulation of the continuous stochastic differential equation, or you're doing agent-based model?
No, continuous stochastic differential equations. We use simulation in MATLAB to add the stochastic part. If you do that for the ONEPs, you get the same. We did it also by varying the parameterization, basically by adding a little difference into the model, by letting the recruitment being proportional to the discovery rate of a proportion, and we didn't find the Weber's law. This was good because at least we didn't find all the time the Weber's law. What we're doing now is actually to study better the parameterization of this model to see in what cases it gives the adherence to the Weber's law, in what case it doesn't. But basically verifying this will what we hope to do is to find the connection between the microscopic mechanisms, so interactions between the individuals, and the macroscopic outcome that is maybe the adherence to the Weber's law. And this is a work in progress, the first part. So, more or less, the take-home message of all this theoretical part is that organisms and superorganisms display similar characteristics and cognitive traits, so it is interesting to look at the dynamics of the behavior of science in order to try to find the parallels in between different systems. Above all, systems as different as individuals and worlds. And basically the goal is to provide a framework in order that can be applicable to many different levels of biological organizations. Now, all this theory can also be exploited to pass from the industrial systems to the artificial ones in order to design, to engineer a system that presents optimal, for instance, optimal behavior in certain conditions, and optimal cognitive processing. So, what we are interested in here is engineering distributed cognitive systems, which are systems made of several autonomous entities that interact and make sense of the outer world. And basically here what we face is the famous design problem, that is, we want a certain behavior of the system as a whole. So we have an idea of what is the macroscopic characteristics of this behavior. The problem is that there exist many different microscopic rules that leads to this one. So which are the ones that fit our system? So the problem is really how to design the rules that are executed by individuals to obtain the desired macroscopic behavior. There was a question? Okay. At the moment there is no general purpose solution. There are many different approaches. There are approaches based on automatic design methodologies like reinforcement learning, evolutionary computation, or optimizations of a system. So you can define a system with some parameters and let automatic methodologies optimize these parameters. Or what I'm exploring at the moment are model-driven design techniques. Some colleagues at the University of Brussels are working on property-driven design. That is, they use model checking formal languages in order to test that certain properties are maintained during the design process. Another possibility is that what I'm exploring right now is cognitive design patterns. Actually, what I did before was to use evolutionary computation, so my research is more or less into this thread, and I'm continuing a little bit on this also. But what I'm presenting now is how to use this concept of cognitive design pattern. So what it is? This is a reusable solution to tackle a problem requiring some cognitive processing. It can be defined more or less broadly like that. Design patterns, cognitive design patterns are loosely inspired from design pattern in software engineering. If there are some software engineers here, you know what design pattern is, like a factory or whatever. These are general purpose solutions that you can apply to different domains, notwithstanding the language in which you're programming and so on. They are really things that you can reuse and can help you in making more efficient, more structured, more robust system. Inspired by this, we try to develop the cognitive design patterns, hoping that they will guide design and development of distributed cognitive systems. Broadly speaking, we can develop a cognitive design pattern along these lines. We have to give a context, that is a set of preconditions that are required in order to implement or to use this cognitive design pattern. We need to characterize a problem and its solution. A problem is the macroscopic description of the system along with the relevant parameterization in order to observe the kind of behavior. And the solution is what corresponds to the microscopic levels, which are the rules, which are the parameters that we have to use in order to obtain the desired behavior. Then, to complete the cognitive design pattern, what we need is a design rationale, which describes you where this idea comes from and how to use it. And some examples that are implementations of this. This whole package given to engineer, to the engineer, can help the engineer to take some ideas and implement it in order to develop a distributed cognitive systems. So, what I will present now is what I'm working at the moment, which is the Stop-Signal cognitive design pattern. In order to present it, I have to go back to the theory and explain you a little bit more about these models of decision making in distributed systems. But however, the context is the collective decision that optimizes speed accuracy trade-off again. and in this case also solve decision deadlocks. I will explain a little bit later what does it mean. The design rationale is given by necessary selection by only these again. Actually, what was observed is that there are cross inhibitions in between populations of these signaling for one or the other side, and this provides some cross inhibition in between the two populations. This is made by what is called stop signals. And basically, well, I'll show you directly the audio, no?
Yeah, there is going.
Okay. These are bees dancing. You see, there is the blue bee that is dancing, and there is the pink one that is giving the stop signal, which is this beep that you hear from time to time. Play it again.
That noise was made by the ants.
So basically, this one is headbanging the other one, and in the same time is giving this beep. This is a video available from this paper from CLA et al. It was published last year on Science, in which they were describing, they made experiments with bees on a desert island, I don't remember where, in order to really control the experimental setup, and they recorded this video as well. What they did is that they painted automatically in pink or in blue the bees that were visiting different sites in order to detect the signals that were exchanging. And they then developed a model which is very similar to the other one. Actually, this is actually exactly the same model I was talking before. That is, you have commitment, with uncommitted individuals can be committed to one or the other side. Decay is if you are committed, you can abandon one of the sides. There is recruitment when one individual committed for one side meets an uncommitted one, then they got committed to the same side, and there is a direct switch. That is, with a certain probability, if A meets B, then they get committed both to A or both to B, depending on the differential quality of the two options. Well, what they've done is that they observed that this is not actually what is happening in honeybees, but it's something like this. There is this cross inhibition. So when two individuals committed for different sides meet, one stays committed to the other and gives the stop signal to the other, which stops recruiting for that side and actually forgets the side and gets uncommitted. What has been shown is that in the case of that which we have this kind of dynamics. If there is one option that is better than the other, then the flow is in this way, everything converges to the whole population committed to this. This is a fixed point. They study the dynamics of the system. If the two alternatives are equal, then there is a deadlock situation. In case there is no decay, so this component is none, what happens is that all the population gets committed and never changes mind. So what happens is that all this line is a stable point, and the dynamics are frozen, with nobody switching. Only when the two options are equal. When the options are equal and you have a decay component, you have a completed deadlock because you have a fixed point appearing here in the middle, which means that 50% are for one option, 50% for the other option, and there is no decision that is taken. And this can go on indefinitely. Then, of course, if you have noise, things may vary, and you can maybe go out of the deadlock if the noise is strong enough. But theoretically, this deadlock exists. When you remove the direct switch and you go to the stop signal, to the cross inhibition, the dynamics completely change. If the stop signal rate is low, you still have a deadlock, but as soon as the stop signal rate is high enough, you have a phase transition. That means that this stable fixed point becomes unstable, and two fixed point appears for the one or the other option. What does this mean? This means that the stop-signal model adaptively tunes the behavior of the system. If there is one option that is better than the other, then a decision is taken always for the best option. But if the two options are comparable, well, the system adaptively switches to a greedy behavior in which you take one or the other options at random. And this is done without the single beast knowing that this really happens. So it's a very powerful methodology to adaptively switch from one or the other behavior. So this is an interesting property, and we can define then our cognitive design pattern in this way. Well, if you have two options, instead of a data switch in between the two, implement a stop signal in order to obtain optimality in the speed accuracy trade-off and automatic resolution of deadlocks. Interesting idea. We have to test it. And it happens that we were studying collective decision making in robot swarms, which present exactly the main features for studying this. Basically, this is an exploitation task in which there are a group of robots that has to navigate into an unknown area from a home location and find some goal locations and get back and navigate efficiently between them. So they have to go back and forth in between two areas. I will fly really over this because I think that time is flowing. And basically, if you give more options, more alternatives, more than one alternative, then what you may experience is that either the colony splits of robots, that is, they are half and half on one or the other option, or they may converge and select only one. In case there is one that is closer, you may want them to exploit the close goal because navigation will be more efficient. In case you have two options of the same quality, well, you may want the swarm to converge anyway because you would like to have all the swarm focused that you don't want to disperse the energy. There are many different reasons why you may want that. But let's assume now that you want to have the swarm currently choosing always one option. What we've done is to develop a very simple behavior in which you basically explore the arena. Then when you find a goal, you record the position, and when you move, you track the position through Odometry. And you try, basically you look in between goal and home. So you enter the goal, you exit from it, then you search for the home, you find it, and then you exit, and you store the position on home and goal. Every robot has only one goal position and one home position. And even if they use odometry, they accumulate error over time, so they can reduce this error by social interaction. This is a broad overview. The paper that we will present on Untitled 2013 conference. Odometry is basically the integration of the motion vector. This is a powerful way to store a location and go back to it. For instance, there is the desert ant that does this when it forages. The ant goes out the nest and makes a strange random path, and it integrates the motion vector over time, so that once the ant finds the food, it goes straight back to the nest in a straight line. This can be done by robots as well.
Sorry, can you repeat this? I don't understand. How the ants can, when it can back go directly?
When the ant explores, it integrates over time the motion vector. So say one step to the left, one step to the right, it means 0. And so this motion vector is integrated over time, so that the ant at every position knows where is home, what is the direction of home, and more or less the distance as well. You can do odometry is a technique that is used in robotics a lot. With the only drawback that given that your sensors are noisy, every time you integrate some more information, you accumulate this noise. At some point, the information you have is completely useless because noise is so big that you don't find that the place you want to find. A nice way to compensate this error is to use the information shared by a swarm of robots. So if you have a swarm of robots that is making navigation through odometry, what they can do is to exchange the information they have. So if robots have the estimated goal position PI, and they have a confidence level, which is basically more or less related to the length of the path they have covered, they can share this information in order to compensate from noise. How to share this? Well, what we have done is to propose 3 different rules to aggregate the information. If 2 robots meet, they share the information they have, and you can aggregate this in different ways. There is an add switch rule in which you take the information with the highest confidence, or a random switch rule for which the probability to take the information is related to the relative confidence level, or simply a weighted average. You just couple the 2 positions and use the confidence level as weight. We have no clue of what are the dynamics that this information sharing creates. So we run a lot of simulations. I'll show you some videos. These are for the switch, and these are the robots navigating, finding the net, the home, and the goal locations, and when they have both, they navigate back and forth. In this case, there is one option that is better than the other because it is closer, and the swarm quickly converges in exploiting only that resource and not the other one. And this is the other switch rule. In exactly the same situation, but with 2 equal alternatives, they are at the same distance. In this case, what we observe is that there is a deadlock, exactly for like decision for us, because the alternatives are equal, so there is no one that is better than the other, and the swarm is not able to take a decision. And you see they more or less oscillate in between committed to one or to the other. So basically, what we observed, we've done a lot of experiments with the 3 rules. This is hard switch, random switch, and weighted average. Here there are different conditions. Here when there is a better option, a short and a long path. Here when we have equal quality options, both close to the nest and both away from the nest. We run thousands of experiments, and we observe that in the case a better option is present, all the mechanisms give you a definite choice for the shortest path. Well, the weighted average makes some errors here. But in case the options are equal, then it's only the weighted average that makes a decision. So 50% of the time for one and 50% of the time for the other. While for the switch, for the other switch rules, we have, and the random switch, we have the deadlock. So no decision. It means that 50% of the robots are for one and 50% of the robots are for others. This is what this graph tells us. So what we observed is that the other switch is the best information aggregation mechanism because it's the fastest in convergence, and it provides the lowest decision error. Weighted average always leads to collective decision, but it is slow and it is prone to errors. And we observed also that R switch and random switch present this deadlock in presence of equal alternatives. Now, what we observe is that we can apply our stop-signal cognitive design pattern to this system because the switch mechanism, R switch and random switch, they both implement a direct switch in between 2 options. So basically the basic model behind is really the one of the direct switch. What we are trying to do, what we are doing now, is to introduce cross-inhibition in between the 2 populations of committed agents to understand whether this can break the deadlock. So that when 2 agents meet, they are advertising for different options. They send a kind of stop signal so that the one with the lowest option in this point-to-point interaction stops being committed to that one and resume exploration. This is the main idea. However, we have to test it. And we want to test it in a very rigorous way. We want to have also some slow, we have the embodiment of the robots that constrains your study. Therefore, we decided to study the application of the cognitive design pattern into this framework by developing multi-agent simulations that abstract the characteristics of this experiment. What we are basically doing is to neglect collisions between individuals. We add a separation component if we want to study the effect of collision avoidance. But basically what we work with is simple kinematics motion model with simple agents, the ideal interactions with neighbors in order to get rid of the sensors of the robots, but try really to study the dynamics of the system. And this is actually an approach that is followed by Vizek, probably you already know, for collective motions. He implemented these particle systems in which and uses statistical physics to study the properties of the system. So what we want to do is something similar to what Vizek did in this context. What we want to do is also to develop a methodology to derive the macroscopic description from the microscopic model and to have analytical tractability. So we are reducing, really, we are going to the essential of the dynamics of the system. And we developed a simulation with agents, implementing the direct speech, so the one that creates deadlock, and we actually found that it is still there, even in this ideal model. And this is straightforward because the model behind, the theoretical model behind, really leads to a deadlock. So there is no population that dominates over the other, even if there is some noisy motion. Then, from this, if we implement then the cross inhibition, we observe that the deadlock is solved, and actually the system converges toward one of the other options. You can see that there is cross inhibition because sometimes the agents change to red when they meet, which means that the committed to one option, which are blue, or the committed to the other option, which are orange, are meeting, and one of the two gets uncommitted. And this is really a simple thing. It is sufficient to break the deadlocks adaptively, and this maintains all the properties of convergence toward the best option when there is one best option available, and so forth. So we are really starting to study this. We did some preliminary experiments. We have to vary also here the parameterization to find the relevant parameters of the models. But for instance, what we have found in the simplest case in which there is no collision at all is that with a direct switch, with a varying number of agents, you switch from a full convergence to the deadlock. That is, if the density is high enough, then there are sufficient interactions in between robots that lead to the deadlock, while spatial factors drive more the dynamics of the system when the density is very low. And when we implement the cross inhibition in the system, the deadlock is broken, and we have a perfect behavior for all the process size. We are still studying this, so I don't have more data, I don't have more details. I don't know why it works, but it works. Only this teaches us that it works. But still, even this simple multi-agent model with simple interactions is very complex to understand analytically. So what we are doing is to reduce complexity and study a multi-dimensional case. We have agents that can move on a ring, so only on one dimension. And actually what they are doing is the same. This is beyond, this is the nest. In this case, they have to choose whether they have to circle clockwise or anti-clockwise. Somehow this is reminiscent to systems of different spins with a particle that interacts. This is, I don't know, I'm yet to investigate this idea of applying the spin classes models to this system, whether it works or not, because in this case we have a complex topology of interaction, so we don't know if this is a good direction or not, but at least the properties of the systems are there. Here we have much less parameters, much less variables, and we can study really the dynamics. Here we have a deadlock. We are still trying to find a way to implement the cross inhibition here in order to have to solve the debit. And we are studying the parameterization. So this is really work in progress, and if you are interested, come to me because we can discuss about that.
Excuse me, do you know if there is a similar result about the role of inhibition to break the deadlock in individual behavior?
Yeah.
Like we have done at the beginning of the talk.
Yeah, there is actually the stop-signal model. The stop-signal was found in the beast by looking at this analogy.
Okay.
More or less.
Yes.
More or less. Stop-signal was hypothesized into the foraging task and was detected there, but it was never detected into necessary selection, mainly for practical reasons, because experiments with these are very complex to run. Given the analogy with if I'm not wrong, I have to read the paper again to give you confirmation, but given the analogy that there was with individual decision making, and there because inhibition is an important factor, they looked into the behavior of bees and they found it. So there is this thing. So basically, what is the expected impact of such a methodology for engineering distributed cognitive systems? Well, we want to provide a general purpose methodology which is really grounded onto theoretical knowledge, onto theoretical investigation. And we are working now on decision making, but what we want to do is to study attention adaptive sampling, and in this case we can look at flocking models, for instance, which in my eyes do resemble to have similar dynamics to attentional dynamics. Then we can extend to categorization, even to learning, because in the end both categorization and learning are deeply linked to decision making. Finally, what we hope is to have enough results in order to feedback some knowledge to biology. That is to discover the relationship in between the individual mechanisms, the parameters of these mechanisms, and the macroscopic behaviors that can tell us some properties of the biological systems. And in the end, this would create a general framework for studying distributed cognition. So, I exhausted myself and you as well, and I thank you for your attention, and I hope you understood.
So, if you are still brave enough, it's time for a question. Actually,
Not bad.
more than an hour, but you can spend at least 10 minutes, 15 minutes as you want for questions.
Or I'm available for some one-to-one interaction.
Do you know the result of a British researcher, a woman, I don't remember the name honestly, that she was investigating how the species of ants that are non-specialized from a physiological point of view in the growth. You know that in the more complex species of ants, the rods are divided like a forager, also physically. But in the middle level of species, the ants can change roles. They can have multiple roles during the life of the nest. And she was investigating how they are deciding to change the role without central control, like this kind of self-organizing system. And they found that there is also famous paper, I think, on science that they are changing role according to the smell of the other ants. Because if an ant is doing, for example, is an explorer, a scout ant, he has obviously very different smells from ants that is doing the nursery, for example. And so, when every ant is encountering another, is somehow counting the frequency of the encountering smell. And so, according to the smells, she can somehow have an idea of what is the situation of the overall nest. If there is a too high density of Stark hole or too low density of Stark hole. And I don't know if you were aware about this.
I know some of these models that some of these task allocation models date back to 10 or 20 years ago, something like that. And yeah, they are quite powerful in describing the system. Related to this, what I want to mention is that in all these processes, all the ants are considered equivalent. Every one is identical to the other one. But this is not realistic. Every ant is different from the other. Above all, every ant has a different threshold in order to get involved in one activity or not. A different threshold for getting recruited, a different threshold to accepting a nest or another one. And this, it is not clear how, but it seems that this heterogeneity into the individual behavior of ants is a fundamental aspect in order to provide an optimal behavior to the whole colony in terms of speed of making choices and so on. So I think that the next step after understanding the dynamics of the simplest model is to introduce this kind of heterogeneity into the microscopic model in order to see what is the impact onto the microscopic dynamics.
I have a follow-up question on this. I was wondering if, Analogies are studied very well also in roles. It is well known that there are Analogies with different roles, for example, warriors or food collector and stuff and so on. And I was wondering if in this diffusion model you were studying they take into account roles, or they just used
No, not yet. At the moment, the model that I show here are simplified models of models that are already quite simple, and they do not take into account all the differences between individual bees. For instance, there is a difference between an ant that is committed to a site and an ant that is just going there in order to evaluate the quality. So there are models that take into account that, but this if you increase the number of states in which your population can be, you increase the number of differential equations and sortability becomes complicated. Still, the relevant dynamics of getting committed or uncommitted are grasped by the simplified models. And you can keep this level of simplicity and add some heterogeneity by another parameter that gives you how likely is that the ant gets committed or not in general, per se. And I guess that some of this can be done and still you can ensure predictability of the system.
Any more questions?
Yes. I'm wondering if in the literature there is some thought idea about how simpler can be the basic element of a swarm to have some sort of cognition inside. I mean, you talk about bees, ants, but also a swarm of bacteria or virus. They show some cognition, so at every level a swarm can become swarm cognition in some sense. Or there is a limit where beyond that you cannot have any more.
So, it is difficult to answer in the context of cognition, but I can answer in the context of complexity in general. You can have a different level of complexity of self-organizing behaviors, but self-organization pertains also to physical systems or particles, so sand, piles, or oil boiling, creating convex pattern of convection. You can't really say that there is cognition into a sand pile or some boiling oil. The discriminant in between systems that can be considered cognitive or not may be into the ability of the individual unit modulate the behavior. A grain of sand or a molecule of oil follows the physical laws, full stop. A swarm of bacteria, ants, bees, population of neurons, there is a kind of interaction with the physical and social environment that lets the system to change the behavior and not only follow the physical law but display more complex dynamics. This is, in my eyes, a discriminant between interesting complex system and more cognitive complex systems, say, and less cognitive ones. Of course, when you talk about cognition, you need to have some interaction with the environment in order to gather information to respond to it. If you don't have that, it's difficult to talk about cognitive systems.
Can I ask a follow-up question to this one? So what you're saying is basically that if you think about it in terms of simple computer science models, that the interesting systems start at Turing machines, which are in internal states that they can change. And then the behavior with respect to the thing depends on the internal state. But if more simple systems where the behavior, they don't have a state like life, several automatons, then in that case you don't have very interesting behavior.
Several automata has been shown to be equivalent to a Turing machine. So, yeah.
Maybe simple automata.
But you can see a finished state machine, our robots are finished state machines. They are not Turing machines, but maybe the difference is that you need many of them in order to get a cognitive system, while a single Turing machine could be cognitive somehow, because it has this internal state processing. But this is tough anyway. Continuing on these analogies may be really dangerous in my eyes. You really need to be careful with the definition that you use. But yeah, it's an appealing analogy somehow.
And if I can do an additional comment, is that I want to ask you something more subjective, not necessarily objective or scientific. For you, how much this kind of dual cognition approach is important today to understand the singular cognition of human beings or animals? Because you show to us some kind of analogical approach. And now I want to know if for you is also somehow necessary to look at this kind of dynamics to catch how the brain works. Then a final additional comment that I want to stress, only because I have personal passion on ants since I was a baby that I was eating ants like a crazy in the garden, is that about the possibilities that these kind of models open to artificial systems. I want to stress on the fact that ants is a very successful animal because, for example, from the point of view of the biomasses, the 60% of the biomasses of the animals in the world are insects. And so insects is somehow the most successful range. And it was proven in many works that in all kind of environments, from the desert to the jungle, ants has always the leader position in any kind of environment. From the point of view of the possibility to take resources or the control, the best position from the climate point of view. So I think that is also interesting to look at this kind of behavior because nature proof that is the most successful from the natural point of view. To express my.
No, I agree because the adaptivity capabilities are so high that they are really worth studying for having the same robustness, activity, and flexibility also in artificial systems. With respect to the first question, difficult to say. My hope is that we can identify the microscopic mechanisms of interaction, the pattern of interaction which are difficult to study in looking at nervous systems, real nervous systems. With electrodes or so on, you have difficulties. The nice idea, the nice fact of insects or these kind of models is that you can really look at the individual-to-individual interactions. And if this individual interaction is rich enough to give you a cognitive behavior that is interesting to study, it can be even similar to the cognitive behavior of brain-based systems, then yeah, I think it is worth, because maybe these microscopic patterns of interactions may be relevant if there is no other way to say that. Otherwise, neuroscience, I'm not an expert of course, and I may say a lot of bullshits in this case, but you are a little bit constrained to the mean field view only, and to approximate patterns of interactions. So I think it is still there is a possibility to give some answer, to feedback some answer also to the study of neural-like systems. It's not really the main goal, should not be the main goal in my eyes, because if you are constrained to that, the risk of failure is really high. So the main goal is, to me, is studying the property of the natural and artificial system and try to make a link in between the two, and I stay at the level of natural swarms and animal swarms and artificial swarms. And in this case, maybe a contribution to biology can be given a little bit more easy.
Any other question? Okay, I think we are satisfied now. Thank you very much, Vito. And we haven't definitive schedule for the next meeting, but there will be more. We are thinking about 4 or 5 more, maybe once per week, and we will keep you posted.